Okay, so today we're talking about Chapter 1, Section 6, Simplifying and Evaluating Algebraic Expressions. So in order to progress in college mathematics, we need to be able to, well, simplify and evaluate algebraic expressions. We need to know what is being asked here, right? And so let's see. I think we're going to snip all of this actually. Alrighty. So from the top, a single number is called a constant, right? Just a number by itself is called a constant. A term is a constant, a variable, or a product and or quotient of constants and variables. So a term is just basically a thing, right? Just a thing written in mathematics. For me, I relate terms as, I mean, a singular term is obviously what it just said, but I differentiate terms by an addition and subtraction sign essentially. But we'll discuss that more as we progress through that. So examples of terms are, and as we see, again, just mathematical statements. They're just terms, right? Without an addition or subtraction, I might add. A number written next to a variable, as in the negative 10x, or variable written next to another variable, as in xy, indicates multiplication. Of course, we've talked about that. If there's no addition, subtraction, multiplication, division sign, then it's an implied multiplication. In the term negative 4x squared, the constant negative 4 is called the numerical coefficient of x squared, or simply the coefficient of x squared. If a term has only one variable, then the exponent of the variable is called the degree of the term. Constants are said to be 0 degree. So we see in the red and all these are just the numbers or the constants, right? And in the black, we have the variable, right? The exponent, this is x raised to the third power, this is y raised to the second power, this is x raised to the first power, and then we have no variable here. We call this a third degree term because it has a variable raised to the third degree. We call this a second degree term because it has a variable raised to the second degree, and so on. If no number is written next to a variable, then the coefficient is understood to be 1. For example, x is equal to 1 times x, which makes sense, right? 1 times anything, anything, if you put anything out there, there's always an implied 1 involved, right? For instance, even this 16 right here, even the 16, there's an implied 1 times 16 there, right? We obviously don't write it because, why stop at just 1 1? We could say 1 times 16. But it's an implied 1, and we use that quite often to do some manipulation of mathematical equations. Like terms or similar terms, we're going to call them like terms though, are terms that are constants, that are constants, or are terms that contain the same variable, if any, raised to the same power. So like terms are our constants or the variables raised to the exact same power. They have got to be raised to the exact same power. And we'll see that here in a moment. Um, let's actually let's put this on that page as well. We're not going to read that, but we're just going to put it on there for notes. So we're going to move this over to the left a little bit. And we'll put like terms over here. And then the like terms continued. Well, or unlike terms down here. All right. So example 1. I feel like we can just snip the whole thing. There's not much to this. Heck, we'll put it on this page. So example 1 reads, identify the like terms in the following list of terms. So 6, 2.2 times x, negative 10.1, a negative x, 3x squared z, negative 5x, 3 over 4x squared z, and 0. One moment. Well, that was a good old sneezing fit. All right, so obviously I guess I didn't have to snip the solution, but we're going to. So we know that 6, negative 10.1, and 0, they are like terms because they are constants. There's numbers, right? Well, now let's say negative 2.2, negative 2, I'm sorry, that's not negative. 2.2 times x, negative x. I was getting ahead of myself. I was looking at that negative. And then this negative 5x, those are like terms because they all have the variable x, and the x is uh, raised to the second, I'm sorry, raised to the first power. Again, I'm looking at the next problem. Yeah, they all have the variable x, and they're all raised to the first power, so they are like terms as well. And then lastly, we have 3x squared z and 3 over 4 x squared z. Well, again, the variables rather are the exact same. They are it's x raised to the second power and the z raised to the first power. So those are like terms as well. All right, so we can simplify algebraic expressions by combining like terms. Uh, we'll be using the associative, commutative, and those properties that we did in section 5 to do this. So combining like terms reads, to combine like terms, add or subtract the coefficients and keep the common variable expression. Alrighty, so let's check out example 2, combining like terms. Alright, so A, combine like terms, 8x plus 10x. Okay, so they both have the variable x, so this could be pretty easy. We just simply add the terms together, 8x and 10x. Excuse me, 8 plus 10 is 18, so we have 18x. B, 6.5 minus 2.3y, 6.5y minus 2.3y plus 3. Okay, so the only like terms here are the ones with a y. So we're going to say 6.5 minus 2.3, so that's 4.2 plus 3. So 4.2y plus 3. Okay. C, we have a 2x squared plus 3x plus x squared minus x. So combining like terms here. And let's actually write this one out because I'm going to show you whenever we get to more complicated problems, I'm going to show you my procedure to go about it. So we're going to go and write out 2x plus 3, I'm sorry, 2x squared plus, all right, first of all, let's go ahead and write it in descending order. No, let's not write in descending order. Let's not. I don't think we've talked about it, so let's not just yet. Okay, later on in mathematics, we're going to have problems like this, and we need to combine like terms. Sometimes you're going to miss a term. Right? Now, here's what we're going to do. We are going to underline. Okay, so what I do is I underline terms that I'm combining. So 2x squared and then x squared is going to be a 3x squared. Okay, and then have plus 3x and then minus x. So 3 minus 1 is a 2, so plus 2x. So the reason why I underline them is so I know that I've used them. I know that I've combined every like term possible. So there are 4 terms here, and I know I didn't skip one. I know I didn't miss one. Now I underline them because I like to be able to look back and see. There are many people, many of my colleagues included, if not all of them, I guess, that like to put a line through them whenever they get done using them. Right? Now, there's nothing wrong with this. My only problem here is that, especially on this, when they're on the computer, there are different colors. But if I were to use the same color white here, and this one might not be the best example. Actually, it's not terrible. Um, they're all the same colors. So like this slash also goes through the slash part of the X, you see. And if I want to go back and see what I did, what the terms were, I feel like the slash is kind of getting in the way sometimes and kind of messes up the way it looks. So I like to underline. Now you can it's your prerogative if you want to underline. If you want to put a slash to it, you can do whatever you want to. But I like to underline so I can see what my numbers were when I used them. Anyways, let's move on. So D, it looks like we're gonna have to do some distributive here. So we're going to distribute that 4 So let's actually write this out as well. Let's move it down. So we have a 4 and then n minus 7 and then plus 5 n plus 1. Okay, so we need to, oh, sorry about that. We need to distribute this 4 right here and right here. Okay, well, what is 4 times n? Well, that's just going to be 4n. 4 times a negative 7, so it's going to be minus 28. And then plus 5 times n is 5n. And then 5 times 1 is 5. Okay. Now again, I use a plus sign here. When I said plus 5n, I probably shouldn't have put the plus beforehand. So let's actually go back and change that. Once I got to this point, I'm done with this part right here. Now I'll move to this part. Well, I'll go 5n. It's a positive 5n, so I say plus 5n. Okay. Obviously, I didn't put it here because 4n. It's just simply 4n. It's not a term being added onto. Gosh, I don't know if I can use the word polynomial or not, but it's not a term being added onto this equation. Add onto this equation, so I don't have to put the plus 4 in there. All right. Anyways, I'm back. Sorry, that sneeze a second ago just tore me up. But anyways, so now we're going to combine like terms. Okay, and I'm just going to put this out here, pointing an arrow to the right because I kind of want to use this area down here at least to get one more problem in. So I'm going to combine my like terms. I have a 4n and a 5n, so that makes a 9n, and then negative 28 and a positive 5 gives me a negative 23. And so that's D. I wonder if I can fit E and F. Well, I can definitely fit E. E is already in simplified form. It has no like terms. Okay, so it's already simplified. So we're going to just skip that. And then F, well, in order to group this, well, remember what we have to do is, or remember what we did rather, when we did the multiplication in section 5, I believe, the previous section, we know that we can essentially rewrite this as 1/2 times, times x plus 3x, and then that's plus 5x. Okay, so all we did was take that fraction out, so it's 1/2 times that. Now, if I were to distribute this, that would be it would be distributed. Yeah, it would be 1/2. It would be x over 2, and then 3x over 2. Right. So we can go about doing that, and we are going to do that actually. But notice how I didn't really change the value of anything. If I were to mush these back together, right, multiply 1/2 times that, I would still get x plus 3x divided by 2. Right. So I didn't change the value of anything at all. And actually, while we're at it, maybe I got a little ahead of myself. I thought we were trying to do an exercise from earlier, and I did the whole thing where I couldn't see the forest for the trees there. X plus 3x. Some among you are probably just like, well, x plus 3x is 4x, Sherman. Yeah, you're right. I didn't have to go that far. I mean, I would have got the same result, but a lot longer. But in this particular case, it's kind of the same thing here. So I've got 4x over 2. Okay, well 4 over 2 is 2, so this ends up being a 2x plus 5x, which is going to be 5x. And if I combine these like terms, well, that's just going to be a 7x. Okay. So yeah, sorry about that. I thought that we were wanting to do the whole division thing from the previous section. Okay, so evaluating algebraic expressions. Again, we're going to snip all these words here, and we'll put them on the notes, but we're not going to read them all. We will read what's in the pink box, though, because that's pretty important. I mean, to be honest with you, it's all pretty important. I'm pretty sure I told you about my best slash worst professor I ever had. Well, the reason was because I was kind of forced to actually look at the textbook, to actually learn from the textbook, which it turns out taught me quite a bit because, well, there's a lot of information in the textbook. Okay, so let's look at the pink box here. So to evaluate an algebraic expression, we need to combine the like terms if possible. We need to substitute the values given for any variable. We need to follow the rules for order of operation. Again, PEMDAS, and let's actually write that out here. So remember PEMDAS. And the note here says terms. Oh, that's not the laser pointer. Terms separated by plus and minus signs may be evaluated at the same time. Then the value of the expression can be found by adding or subtracting from left to right. Of course, we know that. We've done quite a bit of math up to this point. So example 3 reads, evaluate x squared for x equals 3 and x equal to negative 4. Okay, so we need to evaluate for this expression. Well, evaluate for that term, rather. So x squared, we need to evaluate for 3 and for negative 4. Okay, well, for 3, we'll just say, well, it's pretty easy, so we're going to put a 3 in there for x. So 3 squared, well, that's just going to be 9. And then negative 4, okay, so negative 4 squared, well, negative 4 times negative 4 is a positive 16 because 4 times 4 is 16, right? And a negative times a negative is also a positive, so this is going to be a positive 16. B, we have a negative x squared. Okay, so this is a little different. Okay, so first let's go ahead and rewrite this as a negative 1 times x squared. Okay, because we don't have the negative inside of parentheses, right? Now, if this were, let's not talk about it. No one can be too confusing. But anyways, kind of the same procedure. So now it becomes a negative 1 times the 3 squared, which is 9. So we could say negative 1 times 3 squared, which is going to be equal to a negative 1 times 9, which is equal to a negative 9. Okay, and then the same procedure can be done here for a negative 4, right? Again, we can just split this up, same as, I mean, honestly, I'm pretty much going to write the exact same thing underneath it, right? Except instead of writing a 3 squared, I'm put a negative 4. And then times negative 4 squared, which was 16, so we have a negative 1. Let's make that negative better. We have a negative 1 times a positive 16, which is going to be equal to a negative 1 times positive 16, which is a negative 16. Right? And there we just evaluated algebraic expressions. We're going to be doing that a lot. If not in this class, definitely the next class. All right, so this reads simplify and evaluate. So simplify and evaluate. Let's go ahead and simplify this. It looks like I can combine the x's. So it looks like 2x and a 7x can turn into a 9x. So I've got a 9x plus 5. Okay, and we want to evaluate for x is equal to negative 3. So all we have to do is plug in a negative 3. So we're going to have a 9, and then let's put it in yellow here, negative 3 plus 5. Well, 9 times negative 3 is 9, 18, 27. So it's going to be negative 27 plus 5, which is going to be equal to a negative 22. More simplifying. We're just trying to get a little more complicated here. So we've got says simplify and evaluate. So this is rather long. So I'm just going to go ahead and rewrite it a little bit larger so we can see it. And plus, I'm probably going to be doing my whole underlining shtick there. Alrighty. So let's combine like terms. It's not that hard. I need to combine a 3a and a negative 4ab. I'm sorry, 3ab minus 4ab. That's just going to be a negative ab, right? Negative 1ab, or just simply a negative ab. And then I've got a plus 6a minus a, so it's going to be plus 5a. All right, now let's substitute in a 2 for a and a negative 1 for b. So we'd say a negative, and we said 2 for a, so 2 for a and a negative 1 for b, plus 5 times 2. And of course, we're going to be doing this from left to right here, right? So we have a 2 times a negative 1, which is a negative 2, but then we have the negative out in front of it, right? So a negative 2 is going to be a positive 2. And then plus 5 times 2, which is 10, so plus 10. So 2 plus 2, I'm sorry, 2 plus 10 is equal to 12. I believe that's pretty much the last example here. The very last example, which is kind of like a fill in the blank thing. So, ooh, this one looks awful. Okay, actually not. No, that's not that bad. So simplify and evaluate. So 7x plus 5x divided by 4. Well, 7x plus 5x, well, that's just going to be 12x over 4 minus 2 times x plus 1. Okay, well, 12x over 4, I can reduce that, right? 12 over 4, well, that's just 3, so we can say 3x minus, and I guess, well, we actually, no, we don't have to distribute. Okay, and we want to evaluate for x equals to 5, so we're going to say 3, and then we're going to put a 5 in for x, minus 2, and then a 5 in for x, plus 1. Okay, so this is, again, we're PEMDAS, right? Parentheses. So if we do parentheses first, well, 5 plus 1 is a 6. Parentheses, and there's no exponents, multiplication, division, and then now we just read from left to right, right? So this again is a 6. 5 plus 1 is 6. So we say 3 times 5 is 15 minus 2 times 6, which is 12. So 15 minus 12 is equal to a 3. Okay. And that concludes the lecture on Chapter 1, Section 6.